Welcome to Study Loop.
Okay, so 112 is a long one, so let's jump into it. I'm going to start with part A. And here we're given the equation for the number of leaves, or like a minimum number of leaves that a tree would have, as being equivalent to 2 pi times d squared, d being the diameter of the tree, and the surface area of the leaf. So that's the length and width of the leaf. So this is the sort of surface area of leaf. And a more complicated equation for finding this does involve the full area of the leaf. But this, they sort of skip over some of that and just give us the punchline here. So that's what I'll use. And the diameter of tree. Okay, and so then we want to find an equation for the energy exchange and with the transpiration rate relationship using D, L, and W. And so first we need to add some data. And so what would that be? We need to know the energy being absorbed, right? So if we let E be the energy per leaf, free energy per leaf. Then we'd also need to know how many carbon atoms are fixed by that amount of energy, right? So the number of carbon atoms fixed, and we're told sort of in the very beginning that we get 200 and 400 water molecules released per carbon. And so I'm just going to average that at 300. But you can also do this twice and get a range, right? You could calculate at the 200 and then at the 400 and give yourself a range. So we have the 300 water molecules per carbon for our transpiration rate, right? So that's our transpiration. Okay, and then the relationship we can get, then we will want the number of leaves, and that was given to us as the 2 pi d squared times LW. Okay, and multiply that by the amount of energy per leaf, right? So that's going to give us our total sort of intake of energy. Okay, and then that should be roughly equal to our 300 water molecules per carbon multiplied by, do the X, multiply that by our carbon, the amount of carbon molecules that are fixed, right? And that'll give us sort of how much transpiration has occurred. In relationship to our free energy. Okay, and then we move along here. Go to part B. And part B gives us a little story about diversity. Okay, and so what's happening here is on the globe we have our equator and some further away longitudes and latitudes, right? So closer to the North or South Pole. And this is saying that the equator has a greater diversity than some of these systems that are colder. Okay, and one of the explanations for this is the energy equivalence model. So it's the energy equivalence model. Okay, and what does the energy equivalence model say? Well, that says that as free energy increases, so as our free energy increases, the population also increases. Okay, but then as our populations increase, well, then our mutations also increase. Okay, and they're saying that evidence for this model are correlated at the family level diversity of evapotranspiration. So evapotranspiration, if we have so the ground here, and we have atmospheric water, right? So there's some sort of water in the atmosphere. Some of that water is just going to come from evaporating off the ground. So that's our evaporation. And some of it is going to come from transpiration, okay, from the plants. And those two things together make up our atmospheric water. And so this process of both transpiration plus evaporation is the evapotranspiration, right? So it's not really the most clever name you've ever heard, but at least it makes it easy to remember. Okay, so that's our evapotranspiration. And so the idea being that if you're at the equator, right, if you're at the equator, your evaporation should stay roughly the same off of the ground. And so the variance you see across the globe, but at the same latitude, so the variance in region is going to be then due to transpiration by the plants. And so the idea then is that we can use this evapotranspiration to find a correlation at family level diversity. Okay. And so part B wants us to explain this relationship between free energy exchange and latitude, right? And so the idea here then being that this process of this free energy, right, being increased at the equator because there is a lot more like sun energy happening at the equator, right? So you get this increase happening at the equator that you don't see as much of in some of these further away latitudes. Okay, and then so because we have this energy exchange at this increase in energy at the equator, we get the increase in populations. And you also see, say, in rainforest areas, larger sort of populations, right? And then by following the model, this increase in population leads to the increase in mutation. Okay, and that increase in mutation then is sort of the basis of creating the diversity that we see at the equator, right? So it's sort of cyclical here. So the increase in energy gives us this increase in mutation specifically at the equator. Okay, and then we move on to part C, which is giving us some information about specific areas, right? So they are at the same sort of latitudinal area, right? So they're getting the same amount of energy here. But what we're given is we have an Asian ecosystem, and at the family level, it had 67 families, right? Because this is specifically about family level variation. Okay, and then we had a North American ecosystem, And this one had 46 families in it for diversity. Okay, and then we were also given their evapotranspiration, right? And the evapotranspiration for North America was 850 plus or minus 200. And for the Asian one, we have 730 plus or minus 160. Now, the first thing to note is that they're actually, if you take the margin of error into account, they overlap. Okay, but their margin of errors are roughly similar. And so what we see here then is that this Asian population had larger family diversity and a smaller evapotranspiration. Okay, and the North American one had a smaller family diversity and a larger evapotranspiration. So this tells us that, part B suggested that these things are correlated, and it's possible that they are correlated negatively, right? So this would suggest that a greater family diversity actually leads to a smaller evapotranspiration quantity. So in a way, this really does not support the idea that larger family diversity would increase your evapotranspiration.